Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'll start with a quote that I came across recently that I found amusing, and that will give you a clue that it will be mostly about theory, a little bit only about experiments, but I'm not taking such a hard position as Eddington was taking, and the theory I'm going to talk about is hopefully affected by experiments. And anyhow, so this is all about community detection. And community detection is, roughly speaking, the identification of groups of similar objects within an overall population, and based on the observed interactions. So typically, the observation might be a graph of interactions between objects, and this is, of course, closely related with the objectives of clustering nodes in a graph, or embedding the nodes of this graph into some ambient space. And the motivations that I have in mind in this context are the following. They are mostly about recommendation functionalities. So for instance, if the graph is the observed friendship graph of an online social network such as Facebook, one may want to identify latent communities of users with similar interests or profiles, and use those inferred communities to fuel the recommendation engine that will suggest people potential contacts that they may want to connect to. And these contacts, if they have compatible tastes, they will act as suitable filters for relaying information to those users of the online social network. Another similar kind of application, also about recommendation, is when we have data such as the bipartite graph coming from the Netflix ratings of movies by users. So for whichever movie they have rated, they gave it a 1 to 5 stars mark. So we have a big graph connecting users to movies with marks on the edges. And again, we may want to group the users or group the movies. And if we have groups of movies that are similar in a proper sense, then we may want to recommend to users who liked one item similar items. All right, so this is the motivation, but we'll go to an abstract version that can encompass other applications as well. And my outline is the following. I will start off with a generative probabilistic model for studying this community recommendation problem, that is the so-called stochastic block model. And then I will start describing positive results on the performance of what you might call vanilla spectral methods. And subsequently, I will consider harder instances where people do not know whether the vanilla method works, but actually we can save the day by coming up with more involved methods. All right. So let's start with the stochastic block model. It's a very simple random graph model that's been introduced in the 80s by people working on, in social sciences as a means to model social networks. And we have a number of categories and nodes, and such nodes are grouped into categories. We have a fraction of the nodes going into each category. And based on this, we will randomly create edges between the nodes. And the probability of there being an edge between two nodes will only depend on their categories. So here you have this probability. There's a B term which captures the communities the two nodes belong to. And then we have some scaling that is convenient for this purpose, n being the number of nodes. If you ignore, if you look at the average number of neighbors people will have, it will be of order the magnitude of B, which might be constant, times S, so that S is to be thought of as the average number of neighbors in this model. And it's also convenient to think about this average number of neighbors as the signal strength in the observation. And another thing to note is that when we have this model, and if we take the adjacency matrix, we may think of it as being its expectation plus the difference of itself minus its expectation. So there's a noise that is added to a very well-structured matrix, which structure reflects the underlying blocks in the model. Okay, so that's the basic model introduced in the 80s. We may want to augment it a little bit. For instance, there's a very cheap generalization that is convenient if we think of the Netflix price data, which is to label the edges. And so we can just do that by saying, for each edge we had in the graph, we will then draw a label from a distribution that may again depend on the types of the end nodes of that edge. And that yields the labeled stochastic block model. There will be another generalization that is motivated by experiments, actually. That's the stochastic block model with much more general types. Here I've been describing the basic version with a finite fixed number of types. And we can assume an infinite number of types. So for instance, types may be taken from the interval 0, 1. And then, again, we may draw edges according to a kernel that depends on these continuous types. For instance, those numbers between 0 and 1. But apart from that, it's very similar. So here's an example of a shape of how, to determine this function that is the probability of creating an edge between nodes with types x and y between 0 and 1. And again, we can do the trick of labeling the edges. It comes for free. All right. So this has been considered in various papers. Laszlo Lovász has a book on this kind of models, but he was not studying community detection. Instead, he was studying graph limits. When you consider families of graphs and you let the number of nodes go to infinity, in what sense do you have a well-defined limiting object? And these kinds of models are useful to address this question. So let's move on to the performance of spectral methods, and in particular, let's start with the vanilla version. So this consists in the following. You have this adjacency matrix, let's say. So you would just extract the leading eigenvalues and the corresponding eigenvectors. And let's say you take R such eigenvectors. Then you can do an embedding of your n nodes into R-dimensional space by just stacking the coordinates of the eigenvectors that correspond to that. And then you can run in this embedding k-means clustering or any kind of clustering that you may like. And so here's an example of data drawn from the stochastic block model with 4 blocks. So we know exactly how to color the nodes because we generated them like that. And this comes from the Netflix data set, taking R equal 2 in those 2 plots. And so then k-means would color things like that. All right. So a first result in this context is that we'll be able to do well using this approach, the vanilla approach, so long as the signal strength is at least logarithmic in the problem size. And so here's the statement. The spectrum of A has a very special shape, namely there are a small number of eigenvalues that stand out, and we can quantify that. So they are of order of the signal strength S, while the others are of a lower order, namely the square root of the signal strength. And furthermore, if you do the embedding corresponding to these leading eigenvalues, then the representatives of the nodes will cluster according to the hidden blocks. So k-means will do extremely well on this instance. And it's useful to say a few words about why that works, because I'll return to that later on. So thinking back at this picture of the adjacency matrix having this nice structure of a block matrix plus a random noise matrix, here we know that this characterizes the blocks. We know that its eigenstructure is as I described, so namely S order S eigenvalues in a small number, at most as many such eigenvalues as the number of blocks. And so if we could get at this matrix and at its eigenelements, we would get back at the blocks. So the whole game then is to show that the addition of the noise does not affect much this picture. And indeed, this is the case, and this can be shown by using standard arguments on the control of the eigenstructure of a matrix when you add to it a matrix with small spectral radius. So the game is to show that there is a small spectral radius for the noise. And actually, there is a body of literature looking at these kinds of controls, namely at the spectral structure of noise matrices arising from random graphs. I think that the template for the kind of properties we are after is given by this so-called notion of a graph being Ramanujan, which was a term coined in the 80s. And this applies to regular graphs. And graphs are called Ramanujan when the gap between their largest eigenvalues and the second ones is as large as possible. And as large as possible means that you have a jump from the top eigenvalue being ordered the signal strength S here to the square root of that. So this is the template, and it turns out that random graphs tend to have a similar spectral separation property. So for instance, S regular graphs taken uniformly at random have almost this property. So with high probability, they are quasi-Ramanujan. If you take Erdős-Renyi graphs, which are not regular graphs, but have an average, with average degree S, if S is large enough, namely logarithmic, then we have the same kind of behavior. We have a jump from order S to order square root S in the eigenvalues. And the noise matrix corresponding to these Erdős-Renyi graphs has a small spectral radius, namely of order square root S. So this is all we need. We can leverage that, plug it into our model, use some kind of argument to show that this control gives us the control we want. And so this is how you get the positive result for vanilla spectral methods. However, this will fail if the signal strength is smaller than is order 1, say, because then the spectral radius of the noise matrix becomes too large and it dominates the signal, and so it's going to lead to spurious eigenelements, and it will completely destroy the ability to recover the clusters with this method. So if you have labels, you can do exactly the same game by picking random numbers for each label, and so you construct so labels may be categorical, so you could transform them into numbers, and this gives you a weighted adjacency matrix. You can do exactly the same game, and with logarithmic signal strength, again, you will be able to recover the planted clusters exactly so long as the signal is logarithmic. But if you step back and look, say, at the Netflix dataset, you will see this kind of eigenvalue distribution. Whereas if you take a stochastic block model with, say, 4 blocks, you have, as the theory predicts, a gap in the spectrum. And so the theory works well for this, but clearly there's a mismatch. So you don't have this nice spectral separation in data coming from, say, the Netflix data price. So this is one reason to consider general types, and so let's do that now. So with these general types, it turns out that so this is again a reminder of what this model is with general types. So it turns out that in that case, we can again analyze the spectral structure of the matrix we are considering quite precisely. Namely, we can relate the spectrum of the matrix we are considering to the spectrum of an operator that is derived from the model parameters. And it's an integral operator. It's got a number of nice properties. And so I won't detail that too much, but there is a theory one can develop, and one can really characterize how the spectrum of the matrix is determined from the spectrum of this operator. And a byproduct of that is that we can generate spectra that look much more like what the Netflix data suggests. And for instance, we can generate power law spectra, which is a feature that was present to some extent in the Netflix data set. And on top of that, we can make formal claims about the accuracy of the vanilla spectral procedure. Namely, if we do the embedding with, let's say, R eigenelements, we can characterize that this embedding is done according to some distance that, in a sense, is not very far from a distance that is intrinsic in capturing the geometry of the problem. So I will not give a formal statement in that, but I will just show one application. So using the theory we can develop for this, we can show that if, say, we want to estimate the distribution of the label that might have been placed if there had been an edge between nodes I and J in this setup, then we can just do a local averaging in the embedding, and we can control the bias that this kind of procedure will suffer. There's a nice theory, if you like, for spectral methods, the standard ones, so long as the signal strength is logarithmic. And I will now turn to the case where the signal strength is weaker than that, because we have seen that these methods will break for smaller signal strength. So in the weak signal strength case, let's say a signal strength of order 1, we have random graphs of average degree of constant order, then we know that it will not be able to categorize accurately everyone, because a feature of those random graphs is that they have plenty of disconnected nodes, and there's no way we can categorize correctly those disconnected nodes. So we set out to do something a bit less ambitious. Instead, we want to categorize correctly as many nodes as possible. And so this is what this overlap metric captures. It says, let's check how many nodes we have types predicted accurately, but by any scheme we might propose. And we subtract an offset to make sure that if we put every node in the same bin, then this creates 0 for this particular metric. So with this metric for characterizing the performance of any clustering method, one might venture a guess as to what can be achieved. And the guess, the natural one, the naive one, would be to say, well, if I decrease the signal strength, my overlap, okay, will have to decrease, but maybe it will keep on decreasing until the point where I no longer have a huge connected component in my graph. So it's a feature of random graphs that there is this transition between the emergence of a giant component and below this critical connectivity, you have only small connected components. So the naive conjecture is the following one, that you could have a decreasing overlap till you hit this critical connectivity point. But in fact, it's not like that. The picture is more intricate, and this is what I want to tell you next. As you decrease the signal strength, you will hit 0 with any method. The overlap will have to be 0. Even if you have a large connected component in your graph, there will just not be exploitable information in there. So there is another transition point above the critical point for connectivity. So let's go into that. So to explain this, I will describe the simplest possible non-trivial scenario, which is 2 classes of equal sizes. And so we have 2 parameters. There's one parameter characterizing the inter-community connectivity, and another parameter characterizing the so A was intra and B is inter. And so physicists have conjectured this threshold that I was just mentioning in that particular model. They said, well, for parameters A and B that are too close by, then any method will fail to achieve positive overlap. There is just not enough information in the data. Something that was proven in 2012 by Mossel, Niemann, and Sly. But above the transition, this was just a conjecture until last November, actually. And the conjecture was that not only one could achieve positive overlap above this critical value, but that it could be achieved, for instance, by running a belief propagation algorithm or by running an involved spectral method that the authors called spectral redemption. So in November, I developed a proof that I'll describe the results of, the intermediate results of, and this comes with a modified spectral method. All right, and it was this interesting kind of circumstance where I informed all the people interested in this game of the fact that a proof was now available. And the authors told me, well, we are nearly there. And a week later, they came up with another proof, which is very different. So we don't have the embarrassment of having found the same thing. The method and the proof are different. So here's the method I'm using to do informative reconstruction of this model. I'm constructing a derived matrix from the adjacency matrix, which basically counts the number of self-avoiding paths. So between any two nodes I and j, I want to count the number of self-avoiding paths. The typical situation is that there is at most one such path. This is when the neighborhood is tree-like locally. But by definition, it could be more than one such self-avoiding path. So here, between I and j, you have two length 4 self-avoiding paths. So that's the first thing to do, which will be a polynomial time step if you have a sparse enough graph. And based on that, you do spectral analysis on this derived matrix. And so what one can show is that this matrix enjoys a spectral separation that is close to the spectral separation properties I described earlier, a la Ramanujan, if you like. Namely, you have two eigenvalues that stand out. Well, I should say it's for sufficiently long path length. But so you have two eigenvalues that stand out, and the remaining ones are of the order, essentially, of the square root of the leading one. So again, this dichotomy with a square root from the informative eigenvalues to the noisy ones. And the other statement one needs to make use of that is that the second eigenvector in that case is positively correlated with the vector encoding the communities you're interested in. So you can just apply thresholding on the second eigenvector, and this will give you a reconstruction of the planted communities that achieves positive overlap. So some experiments. The experiment confirms the theory. So as I vary my parameters, I see that this overlap metric does kick in roughly at point when the threshold is crossed with parameter tau equal to 1. And what I would like to describe before I conclude is a number of remaining problems. So we have there was this question about a reconstruction down to a threshold where it was not known whether it could be done. We knew it could not be done by vanilla spectral methods, so we could come up with a spectral method that does achieve the goal down to the threshold. But there are many more interesting questions in those models. So here's one. I've talked about this toy model with 2 blocks, so it's natural enough to say, well, what about a larger number of blocks? And we could again have 2 parameters, one parameter for connectivity within a block, and then another for connectivity across blocks. And in that case, when you go to more than 2 blocks, there are conjectures mostly. So here's what we can prove. We can prove that there is a transition above which the modified spectral method I was describing will again achieve some positive overlap, so it will be successful. It is known that if you have not enough information, detection will be infeasible, whatever the method. There will just be not enough information. But it is conjectured that in this setup, there is an intermediate phase where all the known methods, namely belief propagation and spectral methods, will fail, but some more intricate methods, let's say maximum likelihood, which would have a horrendous complexity, will succeed. So that's one of the remaining mysteries. Can one really prove that the picture is like that? So identify these boundaries, something that is not done. And moreover, so proving that reconstruction is impossible is not the hardest part. Figuring out what can be done in the intermediate range is really the challenge here. Whether a polynomial time algorithm can be identified that would achieve useful inference. Here's another interesting open problem on these models. So coming back to a two-community problem, we may consider a tiny community of size k where everyone is connected to everyone. So this is the planted clique problem, if you like. We plant a clique of size k, and we assume for simplicity that all the other edges are present or absent with probability a half. And so it is known for a while that if the size of the planted clique is above square root 10 times a constant, then there are plenty of algorithms that will succeed very easily. Just looking at the degrees of the nodes in the graph will tell where the planted clique is. If you go below square root 10, nothing is known. It is known, in terms of polynomial time algorithms to identify this planted clique. It is known that it will be detectable through impractical algorithms like maximum likelihood or finding the largest clique will give away the clique, but no polynomial time algorithm is known as of now, and it's not clear. So people conjecture, some people like Yuval Perez conjectures that, I don't know if he will back that, but he was optimistic that there may exist polynomial time algorithms, but others take this problem as a measure of the hardness of other problems, saying if a problem is as hard as finding a clique of size, say, n to the 1/3 in this model, then that problem is hard because no one has known how to solve this one. So that's the last open problem I wanted to describe. So to conclude, so vanilla spectral methods are efficient for at least logarithmic signal strength. This is something we can show. Alternatives are needed at lower signal strength. But there are a number of open questions. For instance, belief propagation, which is conjecture to be optimal, does not come with any guarantee. We have guarantees only for in the hard regimes for the modified spectral methods I was describing. As I was saying, it would be of interest to know of computationally efficient methods for the two open problems I was describing. And I have further questions, so I had to cut this list at some point. But one important one is whether the SBM model does reflect correctly real-life data. So we took a step in that direction in going for the continuous types, which allows to fit spectra much more accurately than the spectral block model with a small number of blocks does. But it's not clear yet. It would be good to have evidence from professional statisticians about the accuracy of those models. And with this, I will stop and take questions, if any. Thank you.